Okay, so this is what I will talk about. The work has been done mainly by Bishwajit Maji and Nadia. Bishwajit is in the audience. He will tell you everything. I will tell you about active spinner fluids, and I will show you how they show a variety of interesting phenomena, which we model using the Kahn-Hilliard-Navier-Stokes equation, suitably generalized. The details are in this preprint. Active spinner fluids have been found in a variety of systems. I was showing you the movie for this system, which is a state with magnetic rollers. Here is another schematic taken from the first paper, where you have counter-rotating spinners. The blue go one way and the yellow go the other way. There are biological examples too in this alga and this bacterium. So how do we study these? We study these by using various elements of statistical mechanics and fluid dynamics. Those of you who know about phase separation will have seen this sort of a free energy functional, which is used to study phase separation between two phases. One of them, phi, is negative, the other is positive. Here, negative will mean rotating clockwise, and positive will mean rotating anti-clockwise. But it's a fluid, so we'll keep track of the velocity and the vorticity, and they're counter-rotating. So if you will take my word for it, or look up these papers, there'll be an additional term, which in 2 dimensions can be written like this, tau del squared phi. Tau basically is like the magnitude of the torque, which keeps these things spinning. And in the 2-dimensional case that I will consider, tau and omega both point out of the plane. Okay? So these are the sets of equations which we will look at. We know how to simulate such things using a pseudospectral method. I can go back to that if you're interested. One of the great virtues of this Kahn-Hilliard-Navier-Stokes system is you don't have to put boundary conditions on moving interfaces because it's a diffuse interface model. The price you pay is that there are many control parameters like the Reynolds number, Kahn number, etc. Don't worry about the details. I will just highlight some interesting parameter regimes for you. All right, the first thing is, here is the schematic of the 2 counter-rotating spinners. And if you run the simulation, you will get a picture like this. This is a pseudo-color plot of the vorticity. And if you zoom in on this stuff, you will see it's a type of vortex dipole. And this was known in other studies. And in fact, people had used this when they studied phase separation. And what Bishwajit and Nadia have found, that if the, let me just call it the activity parameter tau, is low, then it goes back to sort of phase separation, which would happen for the good old Kahn-Hilliard-Navier-Stokes. So this is the concentration field phi, and that's the vorticity field. As you increase it, it's sort of something turbulent seems to be happening, and just like conventional turbulence suppresses phase separation, this active spinner turbulence also does it. And then eventually it's all gone, and those of you who are paying a lot of attention will notice that somehow the phi field and the omega field are identical, at least they're proportional. And this has never been seen before, and we have an explanation for it. So, in essence, as we increase the activity tau, first of all, we generate a new type of turbulence. Let's call it active spinner turbulence. And it's a remarkable turbulence in which the vorticity is proportional to this concentration field phi. We can characterize this by all standard measures that we use in turbulence. For example, the energy spectrum, the concentration spectrum, integral scales, coarsening scales. So just let me concentrate on one of these curves. The mean scale, the phase separation scale goes down with activity. That's just what I told you, while the Reynolds number goes up. And there is a statistically steady state. Now, you can do various energy balances. This is how a professional fluid dynamicist does it, but that's not for a 10-minute talk, so I will skip over it. All I want to show you is that if you look at spectra, you don't have to look at the vertical axes. They're compensated in different ways for the experts. There is some sort of a power law regime at low K, and there's another power law regime at intermediate K, and then of course there's dissipation, and the power law seems to become independent of tau, the activity beyond some value like 1.5. So this is a new type of turbulence, if you like, driven not by external forcing, but it's sort of active, and so it's another control parameter. These are, for the experts, these are the fluxes, don't worry about that. But I told you that there's a remarkable proportionality of the vorticity on the concentration field phi, and we can characterize that both by scatter plots, but also if you go back to the spectral energy balance and do a dominant balance, we can actually derive this relation. So omega is proportional to phi. As far as I know, this has never been seen before. And you can say, is your new type of turbulence intermittent? These are fancy definitions for the experts. Short answer is yes. For example, here there is a plot of what is normally called the flatness as a function of length scale L, and you can see that it rises as the length scale goes down. This is small scale intermittency. There is also scale dependence of suitable probability distribution functions. Now, if you change parameters, for example, you change the mean concentration of the thing, you can get a very remarkable phase. First of all, it's made up not of vortex doublets, but of vortex triplets. And as you change this mean concentration, lo and behold, you get a crystal that would warm the cockles of a solid state physicist's heart, because that person would take a Fourier transform and say, this is the reciprocal lattice for a triangular lattice. And it's made up of these basic objects, which are vortex triplets. And you can characterize all that in detail with all these measures, but let me not bother you with details. In essence, we have been able to use this framework to study both turbulence and generated vortical crystals. So with that, let me thank you. I'll be happy to take questions.
Thank you, sir, for such a nice talk. Questions?
Yes, Sriram.
So in the limit epsilon goes to 0, your parameter epsilon.
Yes.
Most of the action will occur only on lower dimensional manifold like lines.
Right, right.
Then it is easy to see why phi and omega should be the same or similar.
I don't know. The epsilon going to zero limit looks good to a theorist, but it is very bad for a simulator, because you have to resolve the...
If the equations can be seen, they may be identical.
No, but we have a rough understanding of epsilon, omega proportional to phi. That comes from the dominant balance on the spectral energy balance. So we have a theory, if you like.
This will be sort of more configuration by configuration equivalence.
It's not exactly that. That's why I showed you a scatter plot.
Okay.
It's not exact. Yes.
So a couple of questions, actually. Can you just show your equations of motion? Yeah. So your tau del squared phi means that in the velocity equation, there's a force density.
Curl of tau phi.
Yeah, so epsilon ij grad j phi. So that means this is a system with a net torque on it, is it?
Well, something is keeping the spinners going, no?
No, what I mean is, is the integral of the torque density 0 or non-zero? That is it like...
I don't think it's spinning around. No. He wants to know.
So,
I know. The whole
my
thing
question is basically, that would mean that there's a stress proportional to phi. Is that right? There's a sigma ij has an epsilon ij times phi in it. So I wanted to know, is the integral of the torque density zero? It's not. So it's like a system with an externally rotating field or something, spinning stuff.
In the experiments, you use a magnetic field to...
Yeah, so I mean, it's different from if you had spinners with a motor.
Yes, right.
Those would not be externally stirred. Those are sort of...
Yeah,
okay.
Many of the realizations in the experiments...
These are rotating magnetic field
Yes,
experiments.
right.
Okay, my other question is that the lattice that you get at the end, you can probe its mechanical response, right? If you wiggle it a little bit.
We tried to fish out your phonon spectrum.
And it'll be different because
It's not working very well because actually for real experts, this is not a crystal, it's a plastic crystal because I couldn't show you the movie. The entities keep on spinning, so it's sort of like a non-equilibrium methane.
Still, but the centers.
Centers, there's hardly any, very little. No, we tried.
Okay.
To the extent, we are still trying, but it's not fluctuating very much. Okay, but yes, translational symmetry is broken. Absolutely.